So now we'll start our discussion with optimizations. That's why we covered this basics for. I'll just again write what did we cover so far so that you have this. So first we understood what is the meaning of integration and differentiation. Integration and differentiation. This we understood. So integration basically, if we just ask me one word, I can say here it gives you tools to compute area under curve. Okay, this tool says you rate of change, instantaneous rate of change, basically instantaneous rate of change. So where are they used in real life? So I said you differentiation is used in so many things. The first thing is, why do we care about these curves? Because I told you that everything, most of the physical phenomena that happen, you can just simulate them and show it in terms of some function. So let's suppose, for example, if you know number of petals in a flower. So this basically follows what's called as Fibonacci sequence. So you can just represent it as T of n plus T of n minus 1 is equal, let's suppose, T of n plus 1, let's say T of n plus 1. So this again expression. So this you can, and similarly if you have, let's suppose, some harmonic motion in the, like, planetary, awesome planets also have that rotation and revolution. You can also have a function for that. So that's why we're interested in these curves, and we want to see what is the change rate of change. Again, for example, if you take a real world example that I just gave you, is the height of people, height of people versus their age. So for example, here we'll see when I was not born, my age obviously was 0. So when I was born, after that, slowly I grew like in the height. So slowly I grew in the height, and then once I became, and this sort of tapered off. So this is a function which represents height in some sort. Okay, this is the height. So everything, most of the things that, most of the physical phenomena that you have exist in nature, you can model them by using functions. You can have a mathematical expression defining them. I was telling you about Einstein. Einstein said that if you have a mosquito going here and there, so that looks pretty much random. So he'll start from here, there, go here and there, like this. This will be the path traced over time. So even Einstein said that you can model this mathematically. You can create a complicated function which can model whole of this process as well. Okay, that's an attempt. That's why we see, now we want to see the integration. Let's leave this aside because we'll take care of this thing, because we have seen the basics. It is used to area under curve. So I wrote under curve. This is area under curve. So differentiation now gives the rate of change, rate of instantaneous rate of change. So that tells me how fast or how slow a thing grows with respect. If I make change in something, so what will the change impact it? So if I have the change in age, so what will the change in height? So let's suppose some people they grow really faster. Okay, some people they grow really slower. So if I want to see average change first, I want to see that is the height of this person growing according to the like average height, growing average height. So for example, let's suppose in the first 2 years, baby should grow, let's suppose, half a meter or something like that, or maybe 0.2 0.3 meters. That's an average growth. So we call this baby is not growing averagely. Why? Because average growth, let's suppose, 0.2 meter, but the rate of change, time, 2 years have passed, but the change in height of this baby is, let's suppose, 0.1. It's not actually the average height. So that's how this change becomes important. So having this background, now we can delve into the world of optimizations. Okay, so we can delve into optimizations. So why this optimization required? That you should first have this, you should have a motivation for this, motivation for learning. Just ingrain this in mind. So far, whatever you have studied regarding the mathematics, you might have felt that these are some mechanical rules. We have to implement them. We have to memorize a lot of stuff, and then only implement this. Mathematics basically tries to explain reality. So it tries to model the reality first. Model the reality. So we'll model the reality, and based on that, it gives a different language to interact with reality and to communicate. Okay, so now we'll see what's the motivation of this. What's the motivation of learning optimizations? Obviously, you have the motivation that will learn optimization, and this will be applicable to machine learning. This will be applicable to deep learning. But there are a lot of things, there are people that use this optimization. If you see investors, so if you know about stock market, if you know about this forex trading, and if you know about these stuff, so there we'll put some money, we'll put some investment. So we'll put some investment in a company, in a stock, or maybe invest in some currency, and we want to get some return. So we invest something and we want to get a return. Now this market, we want to model it again. So okay, what we do is, the objective here is that we want to get maximum investment, maximum return, basically maximum return and less risk. Okay, that's why investors have to optimize. So investors have to optimize their portfolios. If you ask them portfolio, so they invest in different sort of stocks, and when they invest in these stocks, they want to make sure that I have very less risk associated with this, and I can get maximum returns. That is an optimization problem. Okay, again, this is from the perspective of investors. I'll pause the recording because I have to give you some suggestion regarding this. So now you saw that this problem is really important for the investors. Investors want to minimize their risk and they want to maximize their return. Okay, I'm just giving you the motivation. Why should you learn the optimization? It's not only for the machine learning, for the deep learning, but you can use it in the real world scenarios as well. Second thing is that suppose uh, in the future you are having a startup and there you are manufacturing something. So manufacturing. So you want to manufacture something and you aim to maximize your efficiency. Okay, in the design and production. So you want to maximize efficiency. Maximize efficiency. So again, there you will use these optimizations. Even nature, if you see, God is a mathematician. Your Allah is a mathematician, if you ask me. So how is he a mathematician? Because every physical system, it tends to be in the minimum energy state. So every physical system tends to move towards or tends to achieve, tends to move or tends to achieve minimum energy state. This is the premise of nature, how nature works. If you ask me how, so if you see, for example, in a chemical reactor, so these electrons, for example, have the potential energy minimized. And let me give you a real example which you will understand. A ray of light. So ray of light, but it has to travel. So for example, if a light ray has to travel from one point to other point, for example, from point A to point B. So what is the least distance it should cover? So it should go in a straight line. That's why rays of light travel in a straight line. Okay, if they travel, let's suppose in here in this pattern, so it will take a lot of time, lot of distance had to cover, so it will take more time. So it optimizes how to basically minimize the travel time. So it minimize the travel time by following the straight path. So again, if you ask me why are the rain droplets circular? Okay, just have these questions because nature tries to minimize things. Why do things fall downwards? Why don't they go upwards? And things like this. All these things are the simple answers are because nature tries to minimize the energy. It tries to minimize. It tries to achieve a minimum energy state. Okay. So now we need to see. Now I think I have given you some examples by which I think you are motivated to and to pursue this optimizations and why to optimize. Now we'll see how to do these optimizations. Okay, what are some prerequisites? What are the things that we do in this? The first thing that we do in the optimizations is to make this actually is a tool. So this is a tool. Mathematics is a tool. Again, in that toolbox you have another tool. Now I am basically adding tools into your toolbox, and because you are going to be in the real world, that time you should have a strong toolbox. So first we learned algebra. That's again a toolbox. So that's a tool in your toolbox. Now you are learning this optimization. How to make use of this tool. So how to make use of this tool, that we'll learn in the next couple of sessions, maybe 5 to 10 sessions. The first thing is you will have an objective. Okay, you'll create an objective. Okay, a quantitative measure. What is an objective? It is a quantitative measure. Quantitative measure of performance. Let's suppose of the performance. Let's suppose you want to let me give you an example. You want to optimize the stock. You want to optimize your portfolio. So what is your objective? Your objective is that you should buy these stocks which will give you maximum returns, and we should minimize the risk. So you are sort of you first identify your objective, that I have a measure. I want to measure this objective. So my objective is that risk should be minimized and I should get the maximum returns of this. That's the objective of these things. And then you have to model this objective. Okay, this objective can be the profit, let's suppose, in terms of the stock market. It can be the time. I want to minimize the time in terms of this light rays. It can be potential energy or any or the combination of quantities. Okay, it can be anything. Now you know that this objective, it depends on some things. Okay, it depends on whichever you call as unknowns. It depends on unknowns or variables. Unknowns or variables. So your objective depends on some unknowns or variables because you don't know what is going to happen in the stock market. That is an unknown situation for you. Okay, so you'll have to find these unknowns first. That's a goal, and you'll find an objective that depends on the certain characters of systems, and we call them unknowns. So that you'll fit that objective into that. So you have an objective thing. You want to maximize your profit. You want to minimize time or something, and now you try to come with these unknowns, or what are the things that I need to find. These are called unknowns or variables. Okay. Now our goal is to find the values for these unknowns. To find the value for these unknowns. To find the value for the unknown so that this objective gets optimized. Okay, is it clear?
Yes, sir.
So whole of this thing is called modeling. I have been using this term mathematical modeling a lot. So this thing is called modeling. What have I discussed? So you identify a problem first. So you have a problem at hand. Then what you try to do is you try to find an objective. What is my objective of the problem? And then you try to come up with the factors that affect that problem. Okay, that has a contribution towards the problem, and then you try to find the optimal values so that you achieve that objective. So in case of stock market, the objective is to get the maximum profit, let's suppose. So what are the unknowns? So unknowns there are, let's suppose you'll do some analysis on the stocks, how the company is performing from the past, and you will do some, and then you will have different variable. Let's suppose A, B, C, D are some factors which will impact the profit on the company. And then what you'll do is you will try to come up with the optimal values of these things so that your profit is maximized. This whole process is called modeling. So if you ask me what's the modeling is basically a process of identifying the objective, the variables, and one more thing you can add, the constraints also. So you also have some constraint. Let's suppose you want to maximize your profit, but your constraint is you only have 500 rupees. That's a constraint you're putting on it. And you want to maximize your profit, but on the cost, like for example, risk should not be, let's suppose we have a number for risk should not be greater than some number 5. So now you're putting the additional constraints. Okay, so in order to what is modeling? The process of identifying these objectives, these variables, and the constraints for a given problem. That is known as modeling. So again, I'll write it here. This is the process of identifying objectives, okay, and identifying these variables and unknowns which impact this objective, and then these constraints. This is called modeling. Is it clear?
Yes, sir.
Once we have modeled the problem, now you have objective, you have the variables and the constraints. Now your problem is to solve this. Okay, you have to come up with the values of variables such that your objective is achieved. You are optimizing the thing. You are either minimizing or maximizing these things. Okay, and then you use what are called as optimization algorithms. Optimization algorithms you will learn. So by using this optimization algorithm, so these can be used to find the solution. Usually you will use your computer, or maybe you'll use hand to find these optimized solution. So there is no one algorithm. So there is no universal optimized solution. I'll just give you one algorithm and you will say, okay, this is the optimal algorithm which can be used anywhere. So there are a lot of algorithms. There's a collection of these algorithms. So there are collection of these algorithms. That is our primary focus of the course. We want to learn these algorithms. If you have, first thing is we will learn modeling also, how to model problems. And then when we have the problems, when we have the constraints, variables, now we want to solve that problem. Okay, there are a collection of these algorithms. There is no one algorithm. So there is this collection of algorithms by the help of which we'll try to get the optimized answer for our objective function. So each is tailored for a particular type of if you have a particular type optimization problem, and there are different algorithms for that. Okay, now you have to for example, you learn different types of algorithm, then you have to decide which optimal algorithm will work best in that scenario. Okay, that is actually an important choice, because if you choose a really bad algorithm, maybe you will get your optimized solution, it will take a huge amount of time. Okay, and if you take a really good algorithm, it will be really fast to give you the solution. Okay, and sometimes there is no solution. Even some optimal algorithm cannot find some solution for a problem. Okay, this is actually an art to choose. Okay, what should I which algorithm should I pick so that it gives the answer like this. Okay, so we must recognize this. We must be able to recognize whether it has this algorithm has succeeded. Now you applied the algorithm, let's suppose. Okay, now the task is that we should be able to tell whether it has given the optimal solution, whether it has given the optimal. So now this question is there. So now I got some algorithm, I gave it my problem, and it sort of gave me some values for the unknowns. Now I want to make sure that this is actually the optimal solution. How are you so sure this is an optimal solution? For that we have something called as optimality conditions. Optimality conditions. If you succeed, if after the solution these optimality condition are fulfilled, then we'll say that for the current set of variable actually this conditions are satisfied, then it is actually the solution to this problem. So this is the optimal solution. Okay, and there are other techniques like sensitivity analysis and things like that. So the thing is, first we'll do modeling. Now you know what is the process of modeling, so this you'll do first. Then what you will do is, so you'll solve it. In solution, what you'll do, you'll pick an algorithm first, pick an algorithm and solve this, and solve. Then what will happen is, you will test this, you will test is it an optimal solution, test the optimality, is it really an optimal solution. For that you have these optimality conditions. Is it okay so far? Have you understood everything which I discussed? Now we'll see the mathematical formulation. Okay, we'll see this in the part we have this mathematical formulation. So how will we represent this? So there will be x, this x will be unknown parameters, so I'll represent them with x. This will be a vector. Vector basically means a set of x's will be there. Okay, vector, x will be a vector of variables, okay, which we call as also unknowns, as we call them parameters or parameters. That this will be x. Then we'll have f. So f basically will be, this is x and this is f. This will be objective function. Objective function. Okay, objective function, a scalar function of x that we want to either maximize, and we'll want to maximize or minimize this function. That's the only thing that we want to do. We want to maximize the function or we want to minimize the function. Okay, then we'll have some ci. Let's suppose ci is constraints, so we'll call them function constraint or constraints of function. Constraints function, this itself will be a function and it will be constraints. So they are scalar functions that define equation and inequalities. So there will be equations or some inequalities for on this unknown x. Let me give you an example. Let's suppose I'll write minimize for x belongs to Rn. Minimize this function f of x. Okay, then I'll write subject to. Subject to means I'm putting no condition, subject to some conditions. Let's suppose ci of x is, let's suppose, equal to 0. Ci of x is greater or equal to 0 for I is I belongs to some, let's suppose, epsilon or something, and even this I belongs to I. Okay, so this here is an optimization problem now. So here, if you call this is our objective, these x's are our variables are unknowns, and these are our constraints. Okay, and even you can write it like this. For example, if you have you can write it minimize, let's suppose x1 minus 2 whole square plus x2 minus 1 whole square. This is a function subject to constant such that x1 square minus x2 is less than or equal to 0, and x1 plus x2 is less than or equal to 2. Okay, this is again optimization problem. This can be written as like, this can be written in the form of constraint cx. I can write it like this. I can write c1 of x and c2 of x. Okay, this is why constraint. I can write this is equal to minus x1 square plus x2, and I can write minus x1 minus x2 plus 2, and this is I is equal to 1 comma 2, epsilon is equal to 5. Epsilon is equal to 5. Okay, so this is my problem. So f of x here is x1 minus 2 whole square plus x2 minus 1 whole square, and x is equal to x1 x2. I can formulate this problem like this. Think about this problem, how I have written it in shorthand notation. Okay, is it okay? So now we want to find what we call as optimal solution. We want to find the values for this x. So I have written x is equal some x1 x2. I want to find the values for these unknowns. We call that x star. X star are the values, x1 star, x2 star. These are the values on which you will reach the optimal solution. This is what we want to find. X star and x1 and x2 we want to find. Let's start with an example so that you know how to model these problems. Okay, I'll start with the problem, real world problem. So the problem is from the transportation. We call it transportation problem. There are a lot of problems, like planning problem is there. So I'll take this transportation problem. This is a really simplified problem. So what we'll do is, it happens in manufacturing when you have, for example, a really big industry and you are manufacturing something. Let's suppose there is a chemical company. Okay, chemical company has two factories. So we have a chemical company which manufactures some chemicals. So it has two factories, F1 and F2, let's call them. So we have a chemical factory. It has two factories, F1 and F2, and it doesn't retail outlets. So it has retail outlets. Let's suppose 12 outlets. So R1, R2 till R12 are the retail outlets. Retail outlets means where they sell these. Now factories manufacture these products. Now then retail. So they sell these items. They sell these manufacturing things. So then we have, so each factory can produce AI tons of certain chemical. So each factory, let's suppose we have Fi factory, let's say F1 and F2. So it can produce AI tons of chemical as of certain type. Let's suppose chemical type is ith type. So ith factory can produce AI tons of chemicals, A of tons of chemicals. Okay. Each week, let's suppose we'll keep it each week. And then the second thing is, now we'll call this AI is, let's suppose this will be called as capacity. We'll call this capacity. So a factory I can produce AI, and it means AI tons of a chemical each week. I'll say this is the capacity of factory I for this ith chemical. Okay. So then what we have is, so each retail outlet, out of these outlets, we want to see how many they sold. Okay. Let's suppose the demand is BJ. BJ is the demand of jth outlet. Okay. BJ means like these many tons, BJ tons of these. Okay. For an RJ, if you see, for if I take some RJ means the outlet jth outlet. The demand of that outlet weekly is BJ tons of the product. Okay. And the cost of shipping. So you have to now ship the product. You have to ship 1 ton of the product from the factory Fi to the retail outlet. Let's call that CIJ. CIJ is cost of shipping. We want to first analyze, then I'll write them in one go so you understand this. Now the problem, our problem is, if you understood this problem. So what we have, a chemical factory, we have a chemical company, we have two factories. Two factories are F1 and F2. Then we have some 12 retail stores. So we have some retail stores where we sell these products manufactured by these F1 and F2 factories. So about these factories, so Fi, like factory ith factory, produced AI tons of chemicals for some ith chemical. Some ith chemical, for that we produce AI tons of chemicals each week. This is called as capacity. That's the capacity that's the capacity of the factory F1 and F2. Then I have this RJ. If I have RJ means outlet RJ. What is that weekly demand? So weekly demand of jth outlet is BJ. So BJ tons are required. So BJ tons of chemical are required. So cost of shipping is CIJ. This means if you have to ship 1 ton of, if you have to ship 1 ton of the product from factory Fi to an outlet RJ, that is cost is CIJ. So here you are shipping from factory Fi to outlet RJ, and this is the cost associated with that. Now the problem is to determine how much of the product to ship from each factory to the outlet, so it satisfied all the requirements of minimum and minimize cost. So now you see these are some constraints. So we want to minimize the cost, minimize the transportation cost. Let's suppose minimize the cost of transportation. This is our problem. Okay. Now we'll say the variables that we have, this xij, where xi is the number of tons produced and shipped. So we have this xij, and I can be 1 2 and j can be 1 12. I is equal to 1 2 because we have two factories. J can be 1 2 to 12 because we have 12 outlets. So xij, what's xij is number of tons of product shipped from factory I to factory j, factory I to factory j, outlet j. Okay, so this is the number of I'll write it over here, number of, or tons of products, not even number, I'll write tons of product shipped from factory I to outlet J. So this actually, this product shipped, and we want to get the shipping cost minimized. So for each ton, the cost estimated is Cij. So basic optimization, minimize summation of Cij, Xij. We have to minimize it for Ij. This is our optimization function, if you ask me. Is the problem clear first? Tell me, is the problem clear?
Yes, sir.
Again, read it in the problem. We had two factories, F1 and F2, and we had 12 retail outlet stores, R1 to R12. Then we are saying the capacity. The factory I produces AI tons of a chemical each week. Okay. Then I'm saying that Cij is the cost estimated. Cij is the cost estimated for shipping cost estimated if we want to ship 1 ton of product from company from this from factory I to the outlet to this outlet J. So this is Cij. Now I'm introducing this variable Xi. Xi is the tons of product. How many tons of product was shipped from factory I to outlet J? You know that factories are only two, so that's why I is equal 1 comma 2, and you know the J is 12. J goes from 112 because we have 12 outlets. So I said that Xij is the product tons of product that was shipped from factory I to factory J. Now I want to see what is the cost estimated, because you know the Cij is the cost estimated. Okay, Xij is the tons of products that were shipped. It's like if you have to ship, let's suppose 5 kgs. So 5 kg, and for each kg the cost is, let's suppose, 10 rupees. So 10 multiplied by 5, that's 50. Okay, this is for, let's suppose, one factory. And again for the other factory you will sum these things up. So let's suppose we have these outlets R1, R2 and R3 till R12. We have factories F1 and F2. These are factories. So this is sending this some product, this some product, this F2 is also sending some products over here. So each of this will have cost estimated with it. That's why if it has cost estimated, if you are sending 2 tons of product and if the cost estimated is 5, so this will have 10 for like sending product from Fi to R1, F1 to R1 is, let's suppose, 10 estimated with it. Similarly, you will keep on adding these things together. That's what I wrote in a succinct way. Minimize cost multiplied by how many tons of product you are sending. But now you have conditions. So now if you see, we have to minimize this cost, minimize this cost function, Cij multiplied by Xij, I comma j. Subject to constraint. What is the subject? Now we have constraints. Now I'll write constraints. What is the constraint? The first constraint is that this Xij, okay, is less than equal to Ai. What does that mean? The summation of Xij, this j is equal to 1 to 12 is less than, because what's the meaning of Ai is the capacity. So this Ai, this capacity, the producing capacity, for example, if it produces 10 let's suppose tons, a factory produces 10 tons, then it cannot give more than 10 tons. That's why I'm saying the shipping, how many number of tons you are shipping, it should be less than the capacity. That's an obvious constraint. Otherwise you can optimize this function and you can see the factories have to produce more things, but the capacity of factory is Ai, so our production, our number of tons should be less than that. That's the first constraint. Here I is equal to 1 comma 2. That's the first constraint. What's the second constraint? So x of ij should basically be equal to greater than b, greater than equal to bj is demand. So this is our demand. So how much should we supply? We should supply more than demand. Okay, so if you sum this xij over y I is equal to 1 to 2, xij and j is equal 1 comma 2 to 12. So this should also be satisfied. And the third thing is xij is greater than equal to 0. So shipping should be basically greater than equal to 0. You should not ship 0 things. Okay, so now you have to minimize this. These are the constraints. So this is our objective function. These are constraints. The first constraint is that you should basically have this constraint. This signifies this is capacity. You cannot produce more than the capacity of the factory. That's what you are saying, that this equation should be satisfied. That is, capacity should be basically the production should be less than equal to capacity. Okay, you cannot produce more than the capacity. That's the first constraint. The second constraint is you should produce more than the demand. So demand is bj, so you should produce more than the demand. And the third thing is this xij, that is the tons of product should not be equal to 0. It should be greater than 0. Okay, it should be greater than equal to 0. It cannot be negative. Okay, that means it cannot be negative. Is it clear? Did you saw how did we first make an objective function, then we add some constraints?
Yes, sir.
Understood this?
Yes, sir.
Okay, so you just have this also, like we have this factory F1, we have this factory F2. Now it has to send products to these 12, R1, R2 till R12. For each of this there is a cost estimated. Similarly like this, and we want to minimize this cost, the cost toward these, we want to minimize it. I hope now you saw how to basically mathematically model this problem and then how to put these constraints and things like that. So now if you have understood how we have taken a problem and we sort of fit into the mathematical framework of ours, and we made an objective function and we identified these variables. These are variables. So this xij was our variable, this bj was our variable, this ai these were our variables. The Cij, all of these were our variables. So I told you, if you see up over here, so I told you the first thing is modeling. In the modeling, we'll find, if you see the modeling, in the modeling, we'll find an objective and the unknowns or associated with the objective. Then we'll find constraints. So that's what I did. So for the objective was to minimize the cost. That was our objective. We had to minimize the cost. Now I have to see which variables to introduce. So I introduced the Cij, Xij, and I introduced this Ai, Bj, and now I made an objective. This was our objective, and then I put some constraints. Now I'm done with the modeling part. Okay, so I'm done with this part, how to model these things. So if you see it over here, so this is the modeling part. Now I'll have to pick an algorithm and solve it and then test for the optimality. Before going into real world algorithm things, I would like to first tell you the different types of optimization problems. Types of optimization problems. The first category that we have in the continuous versus discrete. Okay, so we have the first type of optimization problem is that continuous or discrete. So in some optimization problems, the variables only make sense if they take integer values. So here they can take a real value. So if you see in this, they can take tons, can take 1.2 ton, 5 ton, 6 tons, and things like that. But in some problems, the integers can, the unknowns can take, if unknowns take integer values, okay, we call it a discrete problem. So why is it used? For example, we'll say for a variable xi could represent number of power plants. So it will take xi is equal 1, 2, 3 integer values. Okay, and in the similar way, we'll say that this these unknowns basically take the integer values, and we call it this discrete problem. Okay, and the second thing is if this takes continuous values, so we'll call it a continuous problem. Problems of this type, or these types of problems, are called integer programming problems that I need not to discuss with you, but I just am telling you that there are different types of problems that we'll handle. If some variables in the problem are not restricted to be integer or binary values, they're sometimes called as mixed integer problems. So first we have integers if all the values are taking integers. Sometimes we have only this integers, and sometimes we have only continuous values. We call them continuous programming problems. And sometimes we have mixed. We have continuous as well as discrete. Some values take, in this problem, if you see, some values take this integer problem. For example, even if I model this problem, we can model it in such a way so that some unknowns take the integer values 1, 2, 3, 4, 5, and some values take a mixed value. So we call that mixed integer programming problems. Okay. So integer programming problems, they're basically type of discrete optimizations. Okay, because the problems may contain non-integer or binary variables, and this is the one type of problems that I want to tell you. This is the first, continuous versus discrete, and it needs more discussion, and we'll see that further. I just want you to know these terms as of now. The second thing that we have is constrained versus unconstrained optimization. So now you saw that we are putting constraints, and sometimes we will not put these constraints. Sometimes the problem will be solved without constraints. I just want to minimize without any constraints. So that time I'll call the problem as constraint and constraint accordingly. So if I'm putting some constraints, I'll call it a constraint optimization. For example, in the unconstrained optimization, we have no constraints. So it directly arises from even the problems with the natural constraints on the variables. It may be safe to disregard them as they do not affect the solution. For example, if you have some constraints and you are saying if we do not work with this constraint, even still the solution will be okay. So you are saying that that is an unconstrained problem. But in the constraint, you are putting some constraint. For example, if you have to impose budgetary things, for example, as I said, that you have, let's suppose, budget of 500 rupees in the investment, rupees 500 on, that's a constraint on you. But unconstrained will be you have unlimited budget, you have no putting maybe you have a budget constraint, let's suppose that is $100 million. But you are saying if I optimize it, I don't need to take care of this constraint. 100 million is very much. I don't need to put it, because you are sort of sure that this won't go beyond, my problem solution won't go beyond 100 million. So in the unconstrained problem, so you are not putting any constraints, or you're ignoring if you are ignoring these additional constraints, you are saying that still I'll get the solution. In the constraint, you are imposing some additional conditions, and you want to basically get the values of the function when you are bound with those conditions. And the third thing is we have global and local optimizations. Global and local optimization. Global versus local, let's call it. So sometimes what you have, a function will have global minima or global maxima. I even showed you this is a function, for example. Here it has a global maxima. Here a function is a global minima. But if a function is like this, okay, it we don't know where is it because we have only view of this much of the function. This means the function is our only view, so we don't know that where is the actual global maxima, so or where is the actual global minima, and sometimes you have to deal with those problems as well. So here we'll see some functions called as convex and non-convex things, and then we'll see, okay, what is the convexity of a function and things like that. I just want you to know the terms. The first thing is constraint, continuous versus discrete, then we have constraint versus unconstrained, then we have global versus local, and then the other is other, I think fourth, it is stochastic and deterministic. Okay, in some of them problems the model cannot fully specify because it depend for example, it depends on quantities. There are unknowns for the time formulation. So many of these, for example, are stochastic problems, because where you have a lot of unknowns and then you have to be probabilistic. You don't have to be deterministic, because basically means you know every variable which impacts it. But for every problem there may be thousands of unknowns. Thousand unknowns will be there, then you cannot model the problem with thousand unknowns. So in order to get that, you have the stochastic process, the probabilistic, because you don't know every unknown in the world. Let's suppose if you want to model this weather, so it will be a stochastic optimization. Okay, there you don't want to optimize, for example, here if you want to optimize your crops, okay, if you want to maximize production of crops, now you know that it depends on weather. Okay, weather is the probabilistic process. Now whole of this will become stochastic process. Again, deterministic means where you know everything. For this factory wala problem we had, so it is deterministic because you have not a lot of unknowns which you can't control, things like that. Okay, so here you will do the best guess basically. Okay, best guess, it all is dependent on the probability, and here we have the deterministic. You mostly know all of these unknowns, and then you try to do the problem. So we have seen four types of problems that will encounter in the optimization. First will be continuous or discrete. Okay, it will be continuous or discrete, otherwise it will be constraint or unconstrained optimization. We'll have global or local, it depends on the function type, and then we'll have stochastic or deterministic problems. And then I think these are the four types, and you can have combination of these. Sometimes you have constraint, then you have, for example, global, and you have that continuous, constraint, global, and deterministic process. So if you have an equation written on that, and you want to see which four categories, like it may be constraint or unconstrained, it may be global or local, it may be stochastic and deterministic, and you will, for example, you have an expression, you will call it is a discrete optimization problem, and it lies in, let's suppose, deterministic, and it is constraint optimization, let's suppose constraint optimization, and it is global optimization problem. Okay, from each of this there will be one characteristics, either it will be discrete or it will be continuous, or it can be mixed. There can be constraint or unconstrained, there can be global or local, or it can be stochastic or deterministic. Okay, so from each of these four folders, let's call it folders, so from each of these folders function will have some property, and we'll call that accordingly, and we'll name it function. I think I'll close this session over here, and I'll take any questions if you guys have, because from the next section onwards, I'll first explain you the mathematical background that is needed to understand, for example, convexity, like things. Convexity, what is convexity, and maybe what is an open set. Okay, what is a norm ball and things like that. And then we'll move on to, if you when you are done with this thing, when you understand this, then we'll model a problem, and we'll learn different types of algorithms and how to sort of apply them, and how to then get the optimized solution, and how to test for the optimality. This is the graph. If you want to find a roadmap, this is my roadmap that I'll follow. I told you how to model things, and we'll now spend a couple of sessions on modeling. We'll take different problem and try to model it. And then I'll also teach you a couple of algorithms. I'll not teach you all the algorithms, but I'll teach you enough algorithm that will be required. And there are simple tests. And this is the thing. So first we'll learn how to model things, and then in the major chunk we'll learn about the algorithms, what are the algorithms, how to solve these things, and accordingly we'll also learn the test of optimality, the sensitivity analysis, and things like that. I hope this section was sort of clear to you and you understood things. And now I'm stopping the recording. So if you have any question, you can ask me.